Uh, Sorry, pardon me for that. So we can start our today's discussion. So right now we are in the week. Banu, can you please unmute yourself? Uh, okay, I'll do that. Yeah. So we'll start with the today discussion. Week 7 content. Okay. So the list of the content that has been covered, and also we'll see that what type of questions are similar to the assignment type of questions which we are going to solve. So those type of questions we are going to see, and at the end, I would also like to encourage you, like, okay, if you have any doubt in this particular entire week 7 content, please let me know. Okay, so let's see the list of the topic that has been covered till now in the week 7. And one more thing I would like to say that I'm on a holiday and I came to my home due to some work at the IIT Bombay. So that's why I don't have access to the printer and all. So I'm writing the things on my own, and so just for this week, we have to compromise with this thing. My handwriting is not that good, but I will try to read everything for you, and we'll try to see what we can do. If there is any word that is not visible and all, then you can let me know. Okay, let's start now. So in this week, we discuss about the phase diagram, different phases that can exist, the most important thing about the metallurgy is that the phase diagram. Every metallurgist is aware about this particular content. So the phases present and the component that are there in the phase diagram that we have discussed. We have seen that how to use the phase diagram, like at what temperature, which phases will be present, and one can alter the composition. One can make things like if someone's desire is to make a component which is easy to make. Okay. Oh, that's is it? It is readable clearly. Oh, thank you, Abhishek. Yeah. If someone's desire is to make things very clear, like some desire to make things like it's material should be easy to melt, then in that case they can go to the eutectic composition. So multiple ways they can use the phase diagram as per their requirement. We have also seen about the phases present in the system, composition of the phases we can find, the proportion of the phases we can find, and then the microstructure evolution we have seen in the isomorphous phase diagram. Isomorphous, we know that both are very easy to mix with each other. They have the same crystal structure, so on and so forth. And we talk about the eutectic system, eutectic reaction, and then the eutectic, hypoeutectic, and hypereutectic order. These things we have to discuss. Then in the end, we discuss about the Gibbs phase rule, which talk about the degree of freedom that is exist for a given particular point. Then we started with the iron carbon phase diagram. In the upcoming week, week 8, we'll focus more on this, especially that eutectoid region. So in this particular week 7 till now, these are the list of the content that has been covered. I would like to ask you that, do you have any doubt in this particular content? If yes, please feel free to communicate. If no, then we'll start with our question. Uh, in any interview, if it is asked, why do we study in the IFE? Why do we study iron cementite phase diagram? Yes, why do we study? Why do we study? See again, the phase diagram can give you the multiple way, like iron cementite. If you are talking about, let's say that your desire is to make a steel, which is let us say having the austenite. Okay, so someone will asking, okay, do something, increase the strength of the steel. I don't know how you will do. So what we know that I have the iron cementite. So here there is some phases will be there. Someone tell that okay, you are having the 0.4% carbon, weight percent carbon. I can also replace this Fe3C with the C. Like it's not going to change things much. And so now let us say your aim is to change the structure, let us say. So from VCC, you can heat it up and you can make it FCC. You can either again further heat it up. And it will give you the multiple variable like, okay, Let us say your strength of the steel is not that much, zero point 0.4. Someone is telling that, okay, go on, increase the strength of the steel. What you will do? In that way, if you want to increase those things, then you will start adding more carbon percentage. Then you will know the idea, okay, if I increase the carbon percent, or you can also, the later on stage, we are going to study about the TTD diagram and the way we can heat treat the things. So those things are going to be very favorable for us if we study this iron cementite phase diagram. It is like this is extremely base on which we are going to build everything. Like even the thermodynamics of the phase diagrams and all are going to come in the later on the weeks. So every metallurgist must be aware about the iron cementite phase diagram. Even there, not only what are the reaction taking place, even the number which is important here. For example, 910, we know that the structure change from BCC to FCC for the pure. So those number, those temperature, those composition, like we know that 0.4% is a eutectoid composition in here. So those things we have to memorize things. We have to keep it in our mind. With the time, it will come, and that was the why we are studying it. And one more thing, like okay, if see someone, people will say that cementite is a hard phase, right? That's very obvious. It's a intermetallic compound. It's very hard. So if you want to increase the strength of your steel, strength of your component which you are going to make, so what you will do, in that way you can go with okay. If I vary the composition of particular material, if you start adding more Fe3C, so your material start getting the more harden and harder. It will get more bitter. So if your application is to resist the indentation, resist any pinning to happen. Okay, let us say someone is like you made a component, and someone is bombarding a ball onto it, okay, with a high speed. So in that case, what you want, it should have that shock. It should be that hard enough to withstand that structure. So in that way, what you will do, you will increase the cementite composition in the ore. Okay, uh, is it clear, Abhishek? Okay. Uh, if there is any doubt, guys, you can always text. You can always put on the comment box. I will definitely respond to it. And if there is no, let's move ahead. Let's move ahead by solving few questions. This week we saw that the questions are will be mostly based on our understanding. It won't involve much of the calculation. Okay. So let's start with the what is the phase diagram. We'll start with the question number one. A diagram that show only the melting of the element. A diagram representing the phase in equilibrium at different condition. A diagram that show only the solid state transformation. A diagram used for the single component system. What do you think? Among this, which one is the right answer? A diagram that show only the melting? No, uh, it's not so only the melting. Yeah, I've said. I've said that the option B is the right answer. That's right. So a diagram represents the phases. Important thing is that in equilibrium, we are talking only about the equilibrium things in the phase diagram. At a different condition can be like a temperature, it can be the pressure, and it can be the composition, particular variable. These are the variables we are having. Okay. So with that, we have solved the question number one. Let's move ahead. What is the term of the what is the term of the temperature above which only liquid is stable in the copper nickel phase diagram? So what do we call? Let us say you can answer these questions. Let us say we are having the phase diagram, which is something like this. Here it's solid, here it's liquid. So they are telling what is the term of the temperature above which only the liquid is stable. So only the liquid is stable. Here we know it's a liquid plus solid. Right? Only liquid is stable is above this particular thing. So what do we call this? So above this particular temperature, liquids are stable. Yes, Abhishek, that's right. Option B is the right answer. That's a liquidus. We call this to be the liquidus. The temperature. Now, if we change the question now, a temperature below which only the solid is stable. Now, in that case, what we are saying that we are talking about, then option A will be the yeah. That's right. So we this one will be the Option A, for the solid to be stable. This one will be the option B, for only liquid to be the stable. That's right. Let's move ahead. Let's go to the next question. Question number three. Is it true or false base? Copper and nickel have the different crystal structure. What do you think? Is it true or false? We are talking more about copper and nickel because it's isomorphous, and in this particular week we discussed about the isomorphous phase diagram. Yeah, it's the false, and they have a same crystal structure, and that is one of the criteria that to perform like Hume-Rodley rule it should satisfy. And they both have FCC. Copper is also FCC, and nickel is also FCC. Second one, in the two-phase region of the copper-nickel phase diagram, both liquid and solid phases coexist. Is it right or wrong? In the two-phase region, that is now they are talking about, if this is solid, this is liquid, they're talking about this region. Two-phase region are there of the copper-nickel phase diagram, both liquid and solid phase coexist. That is true, yeah, perfect. So the we can say that we have solved this. Okay, now water is considered a two-component system because it contains hydrogen and oxygen. What do you think? Should we treat water as one single component or should we treat it differently because of hydrogen and oxygen? So, like they are telling that, okay, what you have a water, should H and O, should we take this as a two different component which is made up of the water, which will form the water, or should we treat water H2 as a one single component? We know that in the water, whenever we are studying about the phase diagram of the water, the H2 is not going to split. It is going to remain a single entity. Whether it can change its phase, like solid, liquid, and gas, it can take those form, but it's not gonna break. It's not gonna split. So it will be considered as a one single component. So not two component. Okay. So the option, this one is a false. A system can have only one phase at a time. What is your opinion on that? Only one phase at a time. Is it that, for example, cementite? Sorry, for example, iron. If we talk about the shale, there we have a ferrite and cementite, two different phases at a same time, right? Can have only one phase? No, right? We know that it can have a multiple phase. In iron itself, in a shell itself, we saw that at room temperature we can have alpha, and we can have a cementite also. So two phase can exist. Okay. So with that, we have solved this question. Okay, it's not that only one phase will be there. Multiple phases can coexist together. Now, let's move ahead. A unary phase diagram represents a system with a two component. What do you think? Option E for the third last one. Urinary phase diagram, a two component. False. Yes. Whenever you think about the unary phase diagram, always keep in mind that water we can consider as example. So this is false, and this is again false. This is true, and this is false. Okay. Let's move ahead. Let's move to the next question. Question number four. A phase in a system is best described as. Now we are talking about the definition of the phase. Okay. So A, B, C, and D. What do you think? A chemically homogeneous and mechanical separable part of a system. A mixture of the different chemical species. A component of the system that can change its composition freely, or solid structure with the same chemical composition. We know that all that's right, Abhishek, that like all remaining things are incorrect. Option A is the right answer. Chemically homogeneous, mechanically separable part of the system. So this is the definition of the phase. This thing is been asked in multiple interview for like the what is the definition of the phase. So we have to keep this in mind. Now let's move ahead. Let's go to the next question. The term component in the phase diagram refer to a component, the independent chemical species that define the composition of a system, the number of phases present in the system, the physical form of the material, the structure defect in a crystal. What do you think? So, where can we use the component? What is the use of the component in the phase diagram? For example, I have the copper, I have the nickel. So these are the two components I have. So now, whatever the phases that are there, let us say alpha phase is there, liquid is there, liquid plus alpha is there. So now this liquid is made up of what? It's made up of copper and nickel, two components. This alpha is made up of the copper and nickel itself. Both again, the liquid and alpha, they are made up of the copper and nickel itself. So the independent chemical species, independent means they don't depend upon each other. Okay, that define the composition of the system. So they, like, let's say we are talking about, let's say this point we are talking about. How can I define the composition of this particular point? So what I can do, okay, I can take the copper, I can take the nickel, I can say, okay, this much percentage of copper and this much percent of the nickel is there at this particular point itself. So copper and nickel, this component can be used to define the composition of the system. Okay, so option A is the right answer over here. That's what Abhishek says. Like for the question number 5, option A is the right one. Okay, guys, let's move ahead. So all the questions are mostly of this particular type. Let's move ahead. Now we'll talk about this mass pair. Okay, alpha iron. Alpha iron will match with which of them? Two phase, two component, BCC, FCC, single component, two component, one phase. What do you think? Alpha iron is the PCC FCC. Yeah, that's right. The A is going to match with the two. Gamma iron will match with the. Go ahead, guys. Yeah, it will be FCC. So this is going to match with the three. Water. Two phase, two component, single component, two component, one phase. Right. Banu sir, if you are having any doubt, please let me know. Or else please mute yourself to avoid the background noise. That's right, Abhishek. So fourth one is the right one over here. I will mute you. Okay. So water is the single component, that's right. So now brine solution. Brine solution is nothing but we are adding H2O and NaCl. So what do you think? Two phase, one component, two component, one phase. Brine solution. See, we are adding two things. These are the two components, water and NaCl. But it will be form the one phase. I was telling that the fifth one. That's right. Because they are going to be dissolved, like salt will dissolve in the water and they will form the liquid solution. It will be the liquid phase only. So it's a two component, but one phase. So D is going to match with the fifth. So the mild steel, which we talk about, it has a two phase. Two phase, we can say that the iron, like or ferrite, you can say, and cementite. So and the two phases are there and the two component. So these are the two phases. And the two component also you can say that okay, two component is the iron and carbon or FeCC. Okay, so with that we can consider it. So D is going to match with the first one. Okay, so with that we have solved this question number 6. Let's move ahead. Let's go to the question number 7. Okay, again, match the pair type only. So now we are having the liquid phase. Okay, A, B, C, D, and E. So now a liquid phase will match with the which of them? A solid solution of the copper and nickel, mixture of liquid solid, ensure two phase remain exist between the single phase, constant temperature lying in the phase diagram, high temperature single phase region. So among these five, which one describe our liquid phase more effectively? Fifth one, right? That's great, I've said. So fifth one is going to match with A. It's a high temperature phase. It's a high temperature single phase region. Now, alpha phase. Alpha phase, you can consider it to be the any solid phase. Okay. Solid solution. So now again, let's say we are talking from the only from the perspective of the copper and nickel this entire stuff till now. So what do you think? So the alpha phase, a solid solution of the copper and nickel will fit perfect because we know that this is our alpha phase. It is consisting of the copper and nickel. They will form a solid solution because we know they are satisfying the Hume-Rodri rule, copper and nickel, and so they one can go in the second place, in the another in the place of the second guy. Like let's say nickel can go in the place of the copper. It can sit at their side, and so it will form a solid solution. So we can say that the alpha is a solid solution of the copper and nickel. Two-phase region. So two-phase region is mixture of the liquid and solid, constant temperature lying in the phase diagram. Ensure two phase exist between the solid and solid phase region. Sorry, between single phase region. Uh, so what do you think? So we are only left with this three. And the best a two-phase region can be defined by the okay, it's a mixture of the liquid and solid. A 1-to-1 rule. This two I wrote by mistake. We have to write TW. So in this particular week, we have studied about various rule. 1-to-1 rule, Gibbs phase rule, Lever's rule, tie line rule. Okay, those things we have discussed. So I've said that it's a three. Ensure a two-phase region exists between between a single phase region. That's right. For example, this is a phase one. This is a phase two. Both are single. In between them, there is a region which is consisting of the two phase. It was liquid alpha. It is the liquid plus alpha. So between the liquid and between the alpha phase, which is equal, like sorry, which is single, there is a phase. There is a region which is existing, which consists of the two phase, both the phases. So this is one-to-one rule it says. And the only remaining part is the isotherm, which is the constant temperature line in the phase diagram. So it will be the option 4. Okay, that's great. Let's move ahead. Let's go to the question number 8. See, I have this type of question, but I have a lot, a lot of this question. So our today's aim to solve the 25, total of the 25 questions. So now if an alloy is in a single phase region, how does its composition compare to the phase composition? So we have alloy, which is single phase. How does its composition compare to the phase composition? Before I before I express, before I tell anything, I would like you to tell me the answer of this. Like the phase composition is a different from the alloy composition. Phase composition is equal to the alloy composition. Phase composition vary across the line. Phase composition is always 50-50 of the binary alloy. So now option B is the right answer. That's great. So Six told that is the option B. Now why? For everyone, why it is that? We have a single phase. Let us say we are talking about single phase. You can take any single phase. So let us say this is alpha phase I am talking about. How does it composition compared to the phase composition? So now let us say phase, this alpha phase is somewhere over here in such a way that we are talking that, okay, 60% nickel is there. So the alpha is consisting of the 60% nickel. If the alloy of is a single phase, how does its composition compare to the phase composition? So the phase composition we got to know. So the composition of the phase and the composition of alloy. What is the composition of alloy? We can say if we are talking about this particular alloy, so alloy will be 68%. We will say that, right? So the alloy composition and the composition of the phase, which is there, is same. Someone told me, okay, bring this particular alloy which is having the 60%. So I will tell the since you're a single phase, the composition of the phase itself will be the 60 itself, right? So with that, we can say that it's the option B is the right answer. So now let's move ahead. In a two-phase region, how do we determine the phase composition? So this was for the single phase. So we are having the two phase right now. How do we define the phase composition? By finding the intersection of the tie line with the phase diagram, by using the atomic structure of the component, by averaging the weight percent of the element, by assuming equal distribution of the component. So for example, what they are telling that, let us say we are talking about this particular point. This is copper, this is nickel. So now at this particular point, what and all are there in this particular region? Liquid and alpha is there. This is alpha and this is liquid. We want to find, we have to find, determine the phase composition. So phases that are present are liquid. And the second phase, which is alpha, solid phase. We need to find in the liquid what is the percent of the nickel. In this, what is the percent of the nickel? So the composition of the, this is the question. So now the question we got to know that, okay, we are having the two-phase region. In that, both the phases, what is the composition of them? In the previous question, we were talking about the only the single phase, so it was not a problem. But now we are talking about the two phases. So in order to do that, what you will do, okay, since you are talking about this particular point, make a tie line, intersect it to the point where the only the liquid is there, intersect to the point where only the alpha is there. So now this thing will give you the composition of the alpha phase, solid phase. What is the let us say this is 70, so we'll say that okay. In this is considered as 70% nickel. Let's say this is the 50 x-axis, so it will be the 50% nickel. So it might be possible that your overall average component, average nickel composition is 60, average all across the line. But the liquid phase at this particular temperature and the solid phase at this particular temperature will have a different composition. So now, how did we did that? We drew a tie line and we find that what are the compositions? What is the composition of each phases? So by finding the intersection of the tie line with the plane boundary, that's what we did. Right? Remaining all things are incorrect. So the question for the question number 9, option A is the right answer. Okay. So let us say, so now let me make more clear about 8 and 9. So here we talk about the question number 9. Here we can say the phase component, the phase composition. What is the alloy composition over here? Alloy composition is 60, average out. This is a phase composition. We can see that the phase composition and the alloy composition, they are different over here. While if I talk about this particular point, any point which is in a single region, whatever the phase composition and the alloy composition will be the same. So if you are in the single phase region, your phase and the alloy will be the same. If you are in the two phase region, they will be different, and that's how it is. Okay, let's move ahead. Let's go to the next question, question number 9. Sorry, question number 10. Question true and false, right? Yeah. So the alloy composition, C naught is always equal to the phase composition regardless of the number of the phases. What do you think? We just discussed something about this. Yeah, Abhishek, that's right. It's a false. It can only be the same only if there is a single phase. So now, in a binary phase diagram, composition can only be represented in the weight percent. Is it that? If you're talking about the binary phase diagram, you can only use the weight percent. No, right? We can use the mole percent also. Phase, we can use the mole fraction, those things. So mole percent can also be used. So this is false. Let's move ahead. In a two-phase region, the phase composition can be determined by drawing a tie line across the region. Is it true? Yeah, that's true. Yeah, see. So now let's move ahead. A tie line in a phase diagram is a vertical line in a two-phase region. Now, what do you say about this? A tie line is a vertical line in the two-phase region. Is it true or false? What we drew? Did we draw the vertical line or the horizontal line over here? This is a tie line, and we know that it's a horizontal line, not the vertical. So it's a false. Yeah, that's great. So this is false. The last one. If an alloy is in a single phase region, the composition of the phase and the composition of the alloy are the same. This is what we told multiple times, right? Yeah, that's right. So this will be the true. Very good. So with that, we have solved 10 questions. We have 15 more to go. We'll try to finish it. All the questions are more or less like this. If we know the concept, within a second, we can solve it. Let's move ahead. Question number 11. What does the term relative amount of a phase in an alloy refer to? Okay, now we are talking about the relative amount. The proportion of the component in the system, sorry, the proportion of the component in a phase. Component, you can say that the copper nickel, if you are seeing from the perspective of the copper nickel phase diagram, you can say that the copper nickel in a phase. The weight of an element in the phase, the atomic fraction of the element in the phase, the proportion of the phase in whole alloy. So among these four, which one do you think is the right one? Now we are talking about the relative amount. So now let us say that I am having, again we will talk from this perspective. This is alpha, liquid plus alpha, and this is liquid. Let us say uh, in this particular composition, 60, this is the temperature. Okay, let us say I am at this particular temperature. So correspondingly, this is the point. This is the point number one. So what is the fraction of the alpha present in this particular point? It's 100%, right? So at this particular point, point number one, we can say alpha is 100%. This is a like alpha. Okay. What about the liquid? How much is the liquid present at this particular point? It's a 0%. So this is the relative amount. Now let us say we are in this particular point, point number two. What is the alpha present over here and the liquid present over here, it will be somewhere in between it will be greater than 0, but it will be less than 100. That's for sure, right? Because some liquid has also formed once I start keep on hitting it. So my alpha will be the less than 100% and it will be greater than 0%. So their fraction is the one which like what is the fraction? Okay, here we told that okay 100%. Here we told that okay it's a 0%. This is the relative amount. So based on that, what do you think? It's a proportion of the component. Are we talking about the copper and nickel? Is it? Or are we talking about the proportion of the phases? So among A, like see, these are the redundant. A, B, and C are the redundant. Nothing to even think about for them. So now here we can say it's a proportion of the phases we will talk about. So the relative amount, this term in the phase diagram is referred to the proportion of the phases, not the proportion of the component. Okay, okay. So for example, here we talk about this copper is this much percent, and this is nickel is 70%, nickel is 50%. This we talk about the proportion of the component in a phase. So in a particular phase, in a particular liquid, what is the proportion of the nickel? What is the proportion of the copper? In the alpha, what is the proportion of the nickel? What is the proportion of the copper we talk about? So these are the option A, the proportion of the component in the phase. While right now what we are talking about, the relative amount, we are talking about the fraction of the phases which are present. How much is alpha is present? How much is liquid is present? Those we are talking about. Okay, let's go to the question number 12. The lever rule is used to determine the composition of the phase in a single phase alloy, the temperature at which the phase exists, the relative proportion of the phases in the two-phase region, the total weight of the alloy. So we are talking about the lever rule. Abhishek is saying that the option C is the right answer. That's perfect. It's the correct. Okay. So by using the lever rule, we can find what is the relative proportion, relative amount of a phase. Let us say whether it's a alpha or it's a liquid in a two-phase region we are talking about. Okay. So this is the question number 12. Let's move ahead. Now, guys, if you feel any doubt now in the questions, please don't hesitate to ask me. Uh, the entire the reason for this particular dot solving session is that you should be able to clear your all the doubts. So let's start with this particular method following. So lever rule. Please let me know which one is the right answer among this. C, D, and E. Just to find the phase composition. Composition equal to the alloy composition contain two different phases. Basic of the rear lever rule. Determine the phase proportion. So we talk about and I've told the answer that okay the lever rule. Using the lever rule, we can find that the phase proportion. So yeah, that's right, Abhishek. It will go to the 5. Now the tie line. What the tie line will give? Just before the lever rule, we talk about the tie line. Does it used to find the phase composition? Composition equal to the alloy composition. Contain two different phases basis of the lever. That is the first one. Right? The tie line will give the uh, it will tell you about the composition about of the particular phases. So what we have drawn over here, this is the tie line. And this tie line is giving that, okay, at this particular point, liquid and alpha was there. Liquid is having this particular composition. Alpha is having this particular composition. Now let's move ahead. Single phase alloy. So now in the single phase alloy they're talking about. Option 2 is the right answer. That's right. That is the composition and the alloy composition and the phase composition will be the exactly same. I should have specified phase composition and alloy composition. Two phase alloy. So in the two phase alloy, What it is to consider the two different phases, it's the basis of the Lever rule. That is three, right? Perfect. And mass balance is the basis of the Lever rule. We should keep it in mind. One can derive this Lever rule if, like, you can see that the Callister book, it has derived that how from the mass balance we can get the Lever rule. Okay, with that we have solved this question. Let's move ahead. Let's move to the next question. Which of the following, which of the following best describe an isomorphous phase diagram? Okay, so now let me read it for you. It might be possible that my handwriting is not that good. It's very bad, I know. So it has the multiple solid phase at the low temperature. Let's draw one isomorphous phase diagram. It's alpha, liquid, liquid plus alpha. It has a multiple solid phase at the low temperature. No, we see only one phase is there, alpha. Incorrect. It has a single solid phase at low temperature. Okay, agreed. At low temperature, it has a single solid phase and a single liquid phase at the high temperature. If we go to the high temperature, so this is the temperature. So from low temperature, if we are going toward the high temperature, we are seeing that only the single liquid phase is there. So the option B is the right answer. We got, okay, yeah. Still, let's move ahead. It has a multiple solid and liquid phase at different temperature. Multiple solid liquid phase, no. There was only one liquid phase and the one solid phase and their combination. That's it. So it's incorrect. It has only a single phase throughout the diagram. It has only single phase. No. If we can see that multiple phases are there. One is liquid, one is alpha. The only thing is that at the low temperature there is only one alpha phase is there, and at the high temperature only the liquid phase is there. So again, this is incorrect. The only answer B is the right answer. Okay, guys. If any doubt, let me know. Okay. If there is no doubt, let's move ahead to the question number 15. Yeah. In a copper nickel system, what happened to the composition of the liquid phase as the solidification progress? In a copper nickel system, you can always respond that what will happen if you are able to get it. So let us say this is our liquid, this is our solid, that is alpha. Here is the liquid plus alpha. So in this particular system, what will happen to the composition of the liquid phase as the solidification progress? Let us say now let us say that this is a point, liquid phase was there. Now we are solidifying it. We are decreasing the temperature. So at this point, the liquid is having that particular composition itself. At this point, also liquid is having the liquid composition. Now let's say we are going below. So now in this, the two phases are there, liquid and alpha, and we know that how we can find the. At this point, the composition will be like this. It will have the alpha. Alpha will have the this particular composition. It will have the liquid. Liquid will have this particular composition. Now we decrease the temperature. We came to this particular temperature now. Now we can say that now the liquid composition is over here and the solid composition is somewhere over here. Now let us say I'm further decreasing the temperature. So now let us say now I'm over here. So what will happen? Liquid will be composition will be this, solid composition will be this. Now what we can see that as I keep on doing that, the composition of the liquid is shifting toward the copper side. Right, it's decreasing. So nickel, let us say here it is 40, nickel is 30, here is 20. So we can say that the nickel composition is decreasing. Another way, another way to look at that, okay, the copper composition is increasing. So it becomes the rich in the copper. So the option C is the right answer. Right. I can alter this question like what will happen to the liquid phase? Instead of liquid phase, I could write what will happen to the solid phase. You can say that, okay, uh, if we keep on doing that, it will again, it will keep on decreasing. More solidify you will get, but it will take after a while, it will take the phase composition. So with that, we have solved this question number 15. If there is any doubt, let me know. If not, we'll move ahead to the question number 15. Yeah, over here. Which of the following is not the reason why alloy are preferred over the pure metal in soldering? So why which one is not the reason? Like instead of pure metal, let us say lead and tin, use lead or use tin. Instead of that, why you are using the lead and tin alloy? Okay, so now it is the higher strength. If the strength is higher, it's a better for us. So this is not the this is the reason that why we are using it. Low melting point. Yes, they are having the low melting point, and due to that only we are using because it's easy to cast them. It's easy to melt them. Okay, eutectic at eutectic point they are having the low melting. So this is also the right answer. They are having the brittle nature. Brittle nature is something which yes, I say that's right. So this is the one which is incorrect and which we are looking for. Right. So with that, we can say that the option C is incorrect and our right answer. Improved mechanical properties. If the mechanical properties is improved, that's the better for us. So we can say that this is the again the correct. So only option C is the one which is desired to us. Let's move ahead. Uh, what is the what is the eutectic reaction in the lead tin system? Now we are talking about the eutectic. Okay. What do you say? What do you think? Which one is the right answer over here? Solid converting to the liquid. Option B, liquid converting to the alpha and beta. That's right. So this is what we can say that it's eutectic. If we see in the phase diagram, having the lead and tin, this is the point where the reaction is happening. That liquid is converting to the it's alpha, it's a beta, alpha plus beta. So this is the way where we are having the liquid is converting alpha beta. So with that, option B is the right answer. Okay, guys, let's move ahead. Let's go to the next question, question number 18. We'll finish in a couple of minutes. I think it won't take more than 10 minutes. It won't take more than 10 minutes. So now, in a hypereutectic lead-tin alloy, which phase form first upon cooling? Okay, so in a hypereutectic lead-tin alloy, which phase form first upon cooling? Okay, it's a beta, liquid, proeutectic alpha, eutectic alpha. Proeutectic alpha, it will form, that's right, of C. Perfect. Like over here, we can say that, okay, this is alpha. Proeutectic means that the alpha which is formed before the eutectic reaction took place. So let us the hypoeutectic they are talking. So we are sure that okay we are in this particular region. And since we are in this particular region, we can see that if I take a liquid, if I start cooling it, the first thing that will happen will alpha will form. And after that, once the temperature get to the desired temperature at which the eutectic reaction take place, then only the reactive then only the eutectic alpha will form. And with that, we can say that proeutectic alpha will form. Eutectic alpha will form later. Though we are talking about which one will the first form upon cooling. So with that, option C is the right answer. And let's move ahead. Let's try some true or false type of questions. So eutectic mixture is a single phase structure. What do you think? False. That's it. A eutectic mixture is consisting of the multiple phase, right? At the eutectic mixture, we can say that two solids are present together, alpha and beta. Hypereutectic alloy contain more thing than the hypereutectic alloy. See this structure. See this phase diagram. Hypereutectic, false. Okay, yeah. Great, Abhishek. So if we see that this is again the false because hypereutectic is having the lower composition in the thing with respect to the hypereutectic. This is hyper. This is hyper. Right. So now let's move ahead. The eutectic microstructure consisting of the alternate layer of the alpha and beta. Is it correct or incorrect? Eutectic mixture consists of the. That's correct. True. Great. In the last one, in the hypoeutectic alloy, hypo, proeutectide beta form before the eutectic reaction. So what do you think on this? Is it true or false? Proeutectic beta will form before the eutectic reaction take place in the hypoeutectic. False. Here the we can say that proeutectic alpha will form. Or if we want to form the proeutectic beta instead of the hypo, you have to go to the hypo. Okay. So again, it's a false. Okay, let's move ahead. Let's go to the question number 20. Okay. The question says that find the degree of freedom at specified point. Specified points are 1, 2, 3, 4, 5, and 6. This is a phase diagram. It is drawn under the consideration that pressure remain constant. So T plus F is equal to the C plus 2. Instead of 2, I will write 1 because pressure is already constant. Only the temperature is there. I need to find the degree of freedom. So I will change it. Degree of freedom is F, which will be equal to the C minus of F plus 1. In all this case, one thing is fixed. One thing is fixed for all the points. That is that C is 2. So that 2. Okay, sorry, minus of P. That's right. Thanks, Abhishek. Huh. So the entire things, C is fixed that C is 2 minus of P plus of 1. So here we can entirely write 3 minus of P. So now let's write for the point number 1, 2, 3, 4, 5, and 6. We have to write the degree of freedom. Oh, I need to fix. So here we can see that for the first one, how many phases are present? So let's label all the phases. It's alpha, beta, alpha plus beta. It's liquid alpha, so liquid plus alpha. Here it will be the liquid plus beta. So now let's write over here that for the point number 1, how many phases are there? So P will be over here. We can say that the number of phases, that is P, is nothing but 2. Alpha and beta 2 are present, right? So P will be equal to that 2, and the degree of freedom will be, then we'll substitute 2 over here, we'll get 1. Now let's go with the point number 2. Point 2 is telling that alpha is there and the beta is there, right? There is no difference. Alpha is there and the beta is there. So again, the number of phases present here are the 2. And with that, if you substitute over here, you will get that the answer is 1. So again, 2 and 1. All right. Now let's move ahead. Point number 3. So actually, what are the phases that are present? We can say that a liquid is there and alpha and beta are there. That is total 3 phases are there at this particular point. So P is 3. If we substitute over here, we'll get 0. Got it? Now, what about the point number 4? Point 4 is telling that I am having only 2 phases. Liquid beta. Above is also liquid. So only the two phases are there. It is the liquid and beta. So phase is two. So it will be the one. Five. Here, five is having the liquid plus alpha. Liquid plus alpha. So two is there. So again the two. It will be the one. Six. Six only one phase is there liquid. We'll substitute over here. Then degree of freedom will be the two. So right. So with that, for all the specified point, we found that what are the degree of freedom will be present. And we use this particular formula, that is the Gibbs phase rule, we have used it. And we substituted, since our system was fixed, since our entire system was fixed that, okay, let's say copper and nickel only is there. Oh, I should not take copper nickel. Let's say lead and tin. Lead and tin is there. So I know that this entire, the component about, regarding the component corresponding to this system is only the two. That is the copper, sorry, that the lead and tin. So I will substitute that part. And then I finalize that, okay, this is my entire formula at the end. And with that, we can solve further, and we got this particular answers. If there is any doubt in this question, question number 20, please let me know. If not, then we'll move ahead. Yeah. So in a binary phase diagram with two phases, equilibrium, the degree of freedom is. So in a binary phase diagram, they're talking about the binary phase diagram. Two phases. Binary phase diagram, it means that we fixed that, okay, two components are there, that is C equal to 2. I was saying that the answer is 1. That's right. Even here also, this was a binary only, and when we saw that there only two phases are there, then the correspondingly degree of freedom will be 1. So the option B is the right answer. Great. Let's move ahead. So now here I'll read it for you. The true and false. First question: the number of degree of freedom increases as the number of phases in the equilibrium increases. Is it true or false? For the last question only, we got to know that f is equal to the 3 minus of p. P is the number of phases. So the question is telling that if we increase the degree of freedom, the number of degree of freedom will increase if the number of phases will increase. True or false? It's a false, right? Because they are like, if we increase, F will decrease. We saw this question, we read it, and we related with the Gibbs phase rule. So at a particular moment, it should strike to us that, let's say you are solving this question in the gate exam. So at that moment, you should realize that, okay, this is corresponding to the Gibbs phase rule. Okay, now let's move ahead. In a single phase region, both composition and the temperature can be independently varied. In a single phase region, okay, both composition and the temperature can be independently varied. Is it true or false? Let us say we are in the alpha, liquid, alpha plus liquid. Single phase region, okay, we are over here. Both composition and temperature can be independently varied. Yeah. So let us say uh, P plus F is equal to the C plus 1. They are not talking about the pressure. We'll consider pressure to be the constant. Number of phases is 1. Degree of freedom is, I don't know. Composition, I know that, okay, they are the 2 plus 1. So we can say that overall degree of freedom is 2. Okay. So with that, we can say that the option B is the right answer. Now, the eutectic reaction is an example of an invariant reaction with 0 degree of freedom. What do you think? Is it right or not? Like eutectic is an invariant reaction and it is having the 0 degree of freedom. Okay, that's true. Just a minute, guys. Just a minute. Yeah. Uh, Pardon, guys. I was at home and there was some noise. Yeah, okay. So it's a true because we know that at the invariant point, total of the three phases were present. We're talking about this particular point. Total of the three phases were present and which is corresponding to the degree of freedom to be zero. So question number 22 is done. Let's move ahead to the question number 23. Which of the following is not a variable in a Gibbs phase rule? Phase composition, temperature, pressure, or phase fraction. So in a Gibbs phase rule, among this, which one is not considered? Phase composition, temperature, pressure, or phase fraction. It has been discussed in the class that in the this phase rule we are talking about the temperature, we talk about the pressure, and we also take into that composition of the phases. We don't consider that the phase fractions. This is not the variable over here. Okay. So with that, A, B, and C are the one which are considered in the this phase rule. And the phase fraction is the one which is not considered. It's not the thermodynamically variable. Okay. So with that, we can say that this is the incorrect one and which is desired to us. What is the maximum carbon content considered in the iron carbon phase diagram? What do you think? Option C is the right answer. Actually, that's correct. Okay. So in the weight percent, we can say that 6.67% is the maximum carbon which we consider in the phase diagram. That's right. Let's move ahead. Now we are left with only two questions. In an iron carbon diagram, which of the following invariant reaction occur at 725 degrees Celsius? Peritectic, eutectic, eutectide, monotectic. Peritectic, we know that liquid plus solid will give another solid. Eutectic, we know that liquid will give the alpha plus beta, two solid. Eutectoid, we know that one solid will give the another solid. And monotectic, we know that one liquid will give solid plus another liquid having the different composition. Abhishek is telling that the B, no, at 725 degrees Celsius, it's a eutectoid which is happening. Why is it that? Here we are having the austenite, and austenite is the one which is transforming to the ferrite, alpha iron, and cementite, Fe3C. So one solid is converting to the another two solids. So option C is the right answer. Eutectic reaction will also take place, but at the higher temperature, where we saw that that liquid will convert to the ferrite and cementite. Like liquid will convert to the iron and cementite. It will occur at the higher temperature. So let me tell you, this all three reactions will take place in the iron, but monotactic is the one which will not take place over here. And at this particular temperature, only eutectoid will take place. We need to keep on remembering at anyway, since we are in the metallurgy or material science field, the phase diagram will come to us like at every time. So with the time we this will grasp in our mind, so we don't have to worry about it. Now, the question number 26, which is our final question today, still typically contain what percentage of carbon? So here we are talking about the steel. Option B, right? That's rate of 6. So option B is the right answer. Less than 2% is a steel. More than that is a cast iron. And the reason why it is a cast iron because that liquid reaction, this eutectic reaction take place in that particular region above greater than 2% of carbon. So with that, we have solved today's questions. Let's have a quick review on that. Like, let's see all the questions one by one. So here our concern was with respect to the phase diagram of steel, and Gibbs phase rule. We solved few questions. Here also Gibbs phase rule only, degree of freedom we talked about. Here in more detail we solved the questions, and then yeah, pro-eutectic alpha and pro-eutectic beta we talk about. Eutectic reaction we talked about, and then we talk about that. Okay, that eutectic reaction, like which one should be, why it is preferred to take that the lead in at the eutectic point, and then again this basic questions on the phase diagram. So most of them are usually based on our understanding how well we went through this particular week, week 7 content. We talk about the lever rule, we talk about the tie line, and phase fraction and phase fraction we talk about, yeah, and relative amount term we heard about it, and I think yeah, phase composition also we talked about, yeah, the component we talked, okay, like water is a single component, while in the brine solution we got the two component, but they correspond to the single phase. Those things that has been done. Yeah. Definition of the component, definition of the phase we talked about, and then the few basics questions on that, the copper and nickel, their crystal structure, those things and you know. Okay. So with that, yeah, this was all, and this was the list of the content that was covered in this particular week. Uh, okay. Yeah. So let me ask you if there is any doubt. Let me know. Or else we can wind up this particular session. If asked what is the limitation of the iron carbon phase diagram, see you can tell multiple things. First of all, iron iron carbon phase diagram. Yeah. First of all, that it talk about the equilibrium things. Like it will like the phase diagram has been designed in a way that after a very long period of time, what is the phase present at particular temperature and particular composition. You took a lot, you are heating it. But for how many hours should be you heat? How many hours should you heat till the 600 degrees Celsius? 1 hour, 2 hour, 3 hour. Phase diagram said heat it for infinite time. Heat it for too long. Like let's say one can say that 100 hours, something like that. So this is the limitation. While in the practical scenario, we know that a certain fixed amount of duration is given. So it doesn't take into the consideration the factor of the time, which is going to be considered in the TTT diagram, time temperature transformation diagram, which we are going to study later on. Okay. So this is the limitation which we can see from our perspective that iron carbon phase diagram is there. Okay, and yeah, is there any other doubt, guys? Let me know. Okay, since there is no doubt, we can wind up today's session. It was great to meet you all. Let's meet again in the week 8. Try to solve that this week doubts. Sorry, try to solve this week assignments. If you face any doubt, see all the questions are most of the more or less we have covered in this particular class. But if you face any doubt now, we can always discuss into the next week. Okay, guys. Bye bye. Take care. Let's meet up again in the next week. Bye to all of you.